Very happy to see all of you at the Aspen Center for Physics. My name is Ramamurthy Shankar. I've been associated with the center for a long time, and I'm right now an honorary member. And I've given some of these public lectures in the past, and I know how much they mean to us and hopefully how much they mean to the people who come here. It's our way of saying thank you to the city of Aspen, which has given us a wonderful home, and also to non-Aspenites, because you're all taxpayers supporting our research, so we want to tell you we appreciate that. Next week, in a couple of weeks, we'll have a lecture by Leonid Murney from MIT on the human genome in 3D. So please try your best to come to that. The task primarily for which I am here is to introduce our speaker. And I don't know who has a more difficult job, because he just has to give a talk the public can understand. And I got to say nice things about Phil that I believe. But I've been working on it, and I've found a way to reconcile my principles with what I'm going to say next. No, really, this is just a joke, and I say it because Phil can take it. I've known him for a very long time, and I'll tell you a few words about him. He's from Tobago. And I verified that personally by going to a conference he organized there. Then he got his bachelor's at Walla Walla University in chemistry. Actually, when he was at MIT, he was a chemist. And then at some point, he saw the light and became a physicist. So we have this rivalry with the chemists. We don't mean anything bad, but when Wolfgang Pauli's wife went with another guy, his only disappointment was that it was a chemist. So we have this view, but we know we need them and they need us, and we get along very well. And in fact, knowledge of chemistry is very important in the kind of problems Phil has been working on, which is on electron transport, or the motion of electrons through different materials. So I will now invite Phil to come and give his talk, which I know will be very clear, because his professional talks, at least, are very clear. In fact, that's how he gets into trouble, because people know what he's saying and they can disagree with him. So the best thing if you're a physicist is to give a talk no one understands and you stay out of trouble. But Phil is very clear, and I'm very eager to see how he handles the mission today. There you go, Phil. He says you can ask questions anytime, right, Phil?
Yes.
Okay.
Sorry about that. Okay. So thank you all for coming. When I got up this morning, I saw it was raining, and I said, excellent. Maybe the talk will be canceled. But you are all very hearty types. So this is my topic. I'm going to try to convince you that the answer to this question is, in fact, yes. Okay, now, my title is in the form of a question, and since it is, I'm reminded immediately of Hinchcliffe's rule. Let me see if this works.
It wasn't working the other day. You might have to.
Okay, I'll have to stand relatively close here. So Hinchcliffe's rule says, Hinchcliffe has asserted that whenever the title of a paper is a question with a yes-no answer, the answer is always no. This paper demonstrates that Hinchcliffe's assertion is false, but only if it is true. And note the author, it's Boris Pion. So copper is something that you know well. It's what every penny is made of. So where's the extra dimension if you're thinking about copper? So let me talk about copper in the context that I am going to propose that, in fact, there is an extra dimension. So copper is a metal. We all know this. And we use it in copper wiring. And it carries a current. And as a result, you can build a circuit out of copper wiring. You can put wires here and there. It will complete the circuit, and this light bulb will come on. Now, what I'm going to be talking about are the electrical properties of materials that contain copper. So let's take a closer look at what is going on in this wire containing copper to get an idea of what electricity really is. So the electrons in a metal bounce around, and this creates this awful property that we're just stuck with in this world, and it's called resistance. And the higher the resistance, the worse the material conducts electricity. So one of the questions that was asked at the end of the 19th century, was what happens if you cool a metal down to very low temperatures? So one of the possibilities is that the electrons just freeze up and they just don't do anything at all. That's a distinct possibility. So people wanted to know what's the answer. And since this is physics, it's an experimental subject, one had to devise a means of obtaining incredibly low temperatures. So first of all, I need to tell you what I mean by low temperature. So is low temperature just the temperature in Aspen during the wintertime? Okay, so since this is a public lecture, I have to define everything. As Shankar says, I tend to be clear. So let's talk about what we mean by low temperature. So if you have a bulb containing a certain amount of gas, and you can adjust the pressure, what happens as you start decreasing the pressure, keeping the volume fixed? Does the temperature go up or down? It goes down. Okay, so this experiment was done a very long time ago, and a graph was obtained. And the graph had 4 points on it. And these are the 4 points. And the temperature was recorded in degrees Celsius. And note, the pressure is in fact dropping, and the temperature is also dropping. And the person who did this is right here, Guillaume Amonton. And I apologize for this picture. It's the only one I could find of him on the web. Okay. One can simply continue this all the way down. It seems like it's a straight line. So the part that we don't know, let's just fill it in with a straight line. Okay, and when it extrapolates to 0, since you can't have negative pressure, that's the lowest temperature possible. What's interesting is this experiment was done in 1850 or something like this, but these points extrapolate to what we now call absolute 0. Yeah, and that's what we mean by the Kelvin scale. So where this crosses this axis, that is 0 degrees Kelvin. And this is room temperature, if you happen to be in a room at this temperature. Okay, so just to give you some sort of calibration, 0 degrees Kelvin is minus 460 degrees Fahrenheit. Okay, so by low temperature, we mean the properties of matter in this regime, not this regime. So the race to 0 had 2 key players. One of those was James Dewar, and he invented the vacuum flask from which we obtained the thermos, okay? And so you need incredible refrigeration if you're going to cool matter down to very low temperatures. And by 1898, he'd pretty much liquefied everything except 2 elements on the periodic table that can be liquefied. The one he didn't do is helium. When he liquefied hydrogen, he got down to a temperature of 20 degrees Kelvin, almost low enough to answer this rather nettling question, what happens to matter at very low temperatures in terms of what the electrons are doing? Now, there was another person whose claim to fame in 1898 is that he was building his lab. Okay, so this is Heikes Kamerlin Onnes in Leiden, in Holland, and he had no results. He had liquefied nothing, okay? But in 1908, he liquefied helium. And he obtained a temperature of 0.9 degrees Kelvin, which is exactly the regime you need to be in to answer this question: what happens to electrons at very low temperatures? Once Dewar learned about this, he realized his future in low temperature physics was completely over.
I think it's a do or die situation.
Yeah, right. Yeah. That was the last paper he ever published in low temperature physics. And from that point on in his career, he started studying the surface tension of bubbles. So the field now was left entirely to Heikes, Kamerlingh, Onnes, and theoreticians produced lots of interesting predictions as to what would happen to the resistivity at very low temperatures, or the resistance. Some said it would go to zero. Some said, as I had pointed out, that the electrons might just freeze out and the resistance would just go off to infinity. And these are fairly famous people who did this. Well, the experiment was done, and here's what they found. It's really his assistant who made this particular measurement. The resistance looks fine, but it drops to zero at a particular temperature. And this is 4.2 degrees Kelvin. The first metal in which superconductivity, this dropping to zero, is referred to as the phenomenon of superconductivity of the resistance. And the first metal was mercury. They did this in 1911. This was such a startling effect, it immediately won a Nobel Prize just 2 years later. Okay, now superconductivity solves a major problem with the transmission of electricity from a power plant to your home, or because a lot of the loss in the transmission of electricity is in fact loss. But the loss is minimized in a superconductor because one is carrying current without any resistance. And so this is an incredibly economically valuable field, and that's one of the things that motivates research in superconductivity. Another thing that makes superconductivity incredibly unique is that superconductors are the only materials around that don't like in which if you were to put a magnet above a superconductor, it would just hover there forever. So there's an interaction between a magnetic interaction between a magnet and a superconductor, which keeps the magnet fixed at a certain distance. And this is true even if you were to, for example, flip this thing over, because magnetism is way stronger than gravity. And I hope this works. Yes, that's right. So here it is flipped over, and this principle, for example, allows you to have, once you just give this a kick, it just moves along a track. So this is the magnet, this is the train. You can see the steam coming off here, the refrigeration. Okay, so superconductivity is an incredibly important and physically interesting phenomenon because of these two effects. This was explained at my home institution, the University of Illinois, in 1957, and they were awarded the Nobel Prize in 1972. There are two key aspects of this theory. This is a thermometer indicating temperature, so temperature is decreasing this way. What they said is that at very high temperatures, the electrons in mercury are free. They move independently, and you don't need to worry about anything more than that. Just treat the electrons as independent entities. But at low temperatures, what really causes superconductivity is that the electrons arrange themselves in this very coherent state. And in fact, if you want to scatter or disrupt this whole state, you would have, if you wanted to disrupt this low temperature effect, you would have to scatter all of the electrons. And that's a probabilistically incredibly rare event that it would never happen unless you were to increase the temperature. So in the superconducting state, this is completely impervious to any sort of disruption that would normally be in a metal. And that's the origin of superconductivity. Now, superconductors, this is a timeline of superconductivity and the temperature at which things were observed to superconduct. This is mercury, 4.2 degrees Kelvin. And you need incredible refrigeration. You need liquid helium. As one goes along, the temperature started to increase. We have the BCS theory. But something really happened here in 1987. The temperatures have quadrupled. And this was the Woodstock moment in physics in which everyone started working on this problem. And that's when I really got interested in solid-state physics, was because of this singular event. Now, why is this important? It's important because this is the line at which refrigeration becomes cheaper than buying beer. Okay? Liquid nitrogen is cheaper than beer, and hence refrigeration is incredibly cheap now. Before, to study low-temperature physics, you needed to go and collect helium, liquefy it, but you don't have to do that anymore. So these superconductors now are accessible with incredibly cheap means. And in fact, some are putting this to use in transmission from power plants to power plants. And so here is the, I think this is this material right here. And these are cooled by liquid nitrogen. So these kinds of transmission lines is ultimately what one would like to replace almost all the copper wiring in the US with. But technically what you would like is something that didn't work at 77 Kelvin, but at a higher temperature. So every year we encounter lots of claims of superconductivity at incredibly high temperatures, and typically many of these end up being false. So USO corresponds to an unidentified superconducting object. And but the materials I'm going to talk about are the ones right here, which have copper. So here is a crystal structure of one of these materials, and these green things are the coppers. If I put mercury next to this, I can ask a very simple question. Can superconductivity in both of these materials be solved in the same way? If it could be solved in the same way, I wouldn't be here. And this conference that we're attending at Aspen wouldn't be going on. Now recall what Bardeen, Cooper, and Schrieffer said. At high temperatures, the electrons just act independently. And at low temperatures, that's when the real business happens. Okay, so the thing I want to answer right now is, when can electrons be treated as independent? Okay, so electrons can do two things. They can just move by themselves without any disturbance from anything else. And when they engage in this sort of motion, this is called the kinetic energy. And this is related to the momentum, another concept which I will get to. But electrons, as you know, are charged, so they can repel one another. And this is the really bad part. This has to do with the interaction energy. Now, every material has a ratio of how big the interactions are, so things that are not independent, to the part which is completely independent. Okay, so the crucial ratio for any material is its interaction relative to the kinetic energy. For standard metals, this ratio is less than 1, which means this thing is much bigger than this, and that's the situation with mercury. For the situation in the copper oxide materials, this quantity is much bigger than 1, which means the interactions are the things that is dominating the physics. It's not just the independent motion. It's the behavior which comes about from the collection of these electrons. And understanding that is what we call a problem at strong coupling. Strong coupling just means the interactions are bigger than the kinetic energy. Okay, so the paradigmatic materials for both of these limits are mercury and this particular copper oxide superconductor. Okay, so the physics of strong coupling. So we can't treat the electrons as being independent. Some sort of collective phenomena emerges. And this comes about because the whole is bigger than the sum of its parts. So the problem in understanding superconductivity in this material is that we can't start with the system. We can't, this assumption that the electrons are free and we can treat them independently is no longer valid. We have to solve a problem with strong coupling, and out of that, we have a superconductor. And this is the big question. And it's remained a question since these materials came on board in 1987. So the problem is we have this funny metallic state in which the interactions dominate, and I call this strange metal. And this problem has been around for about 30 years. Okay, now this problem requires new tools. It requires that we sort of develop methods for treating what electrons do when the interactions between them dominates. So let's look at all of the tools we have for treating physics in this regime. Okay, so here are a list of all of the tools we have for treating electrons in this regime. Okay. We don't really have very good tools. Okay? And when you don't have tools, what you can do is guess. Okay? And the power of your guess, or the ability, essentially the success of your guess is really governed by your ability to convince people. And that's largely determined by your ego. Okay. Now, if your ego is very large, physics is based on a small parameter. So then you can do an expansion. Okay, so 1 over your ego is an incredibly small number. And you can develop, I think this is your joke. Are you the one who originated this joke? Yes. The 1 over e, yes, okay, so this is Shankar's joke. Okay, the 1 over ego expansion is a highly convergent series. Okay?
Even Mr. Trump is a physicist.
Yeah, that's right. Okay. Okay, so yeah, one can develop the 1 over ego expansion. Okay, now short of doing something like that, since I live in the Midwest and we have to sort of back up our claims with serious calculations, perhaps the answer lies with string theory. Okay, so let me try to, and the major claim of string theory is that the basic building blocks of nature aren't things that we thought they were. They really are these things that have a certain finite extent, but they're certain vibrations. Okay, so let me try to motivate how it is that a certain claim of string theory might give us some purchase in understanding what the electrons are doing. Now, to do that, and since I tend to explain everything, let me just take a step back and have a little interlude on packing. Okay, so you're throwing balls into a bin. What determines how many balls can fit into this bin? Is it the area of this bin, or is it the volume? It's the volume. Excellent. So you're all very good physicists. Okay, it's the volume. So the packing, and we have this notion, right? It's very intuitive. The capacity of any object is determined by its volume. Okay. Now, let's use this same intuition in the context of a black hole. Okay, now I haven't drawn anything about the interior of this black hole because that's where all of the controversy is. But there's no controversy about what a black hole basically looks like as far as the point of no return. Now, let's assume that you were very unfortunate and you lost your wallet and your excuse was that it dropped into a black hole. Okay. It turns out all would not be lost. Because one of the things we all agree on is that there's no information lost. What happens is your wallet reappears on the boundary. In fact, everything you pack into a black hole, all of the information you throw into a black hole, the content, the capacity of a black hole is determined by its surface area. It's not determined by its volume. So it's very different than throwing things into a bin. However, the reason why there is this disconnect between what's the bulk physics of a black hole and the surface area is that you need quantum mechanics to understand how you would actually figure out that it was your wallet that dropped in. So the rules for understanding what is going on the boundary of this black hole are determined by a very different rule than the thing that allowed your wallet to fall inside the black hole to begin with, namely gravity. Now, this has been formulated as an incredibly elegant conjecture in which the surface degrees of freedom of a black hole encode the physics of what's going on inside a nucleus. This was the original form of the conjecture, that black holes tell us about the strongly coupled degrees of freedom inside a nucleus, and I call those the nucleons. So that we have an equality here between things which look very different. So let me just be more focused about this. We have an equality, and on one side of this equality, we have gravity. And I'm going to talk about gravity in the context of general relativity, where we replace masses with curvature of space-time that pervades the whole universe. So we have curvature, and we can't induce anything really about the curvature by looking at some small point. We have to look at really long distances. So we have a geometrical problem here, and this is now equated to an algebraic problem involving quantum mechanics. Quantum mechanics is about the very small. So we see there's an obvious disconnect. So if we're trying to understand how it is that these things are equal, there's an obvious difference here. This is about the very large, and this is about the very small. Now, how do we tell an object is large? Do we stand very close to it or far away from it? We stand far away so that we can get some perspective on the object. Okay, whereas, and hence, if we were to try to touch it and make some sort of local measurement, we couldn't really infer the size of the object. But small things, we can just go and reach in and touch them, makes all sorts of measurements that we want, and hence, size does matter in this case, and it in fact can be formulated in a certain principle, namely, that any theory with gravity has less observables than a theory without it. And hence, one is immediately struck then, what do we really mean by this equal sign? Because it seemed like the stuff over here is very different than the stuff over here. Okay, now anytime you have an equal sign, I was talking about equal signs with my daughter this morning, that anytime you have an equal sign, you're saying this is this. But the question is, we really don't know what is means in this case, which brings up this I don't need to say anything more about this, okay? We really don't know what is means, okay? And, but nonetheless, I want to ask the question, okay? Is quantum gravity, these surface degrees of freedom of hugely gravitational objects, is it equal to the strange metal? Okay, that's the question. Okay, now how would we go about answering this question? Okay, so we know that we're trying to deal with a problem in which things are strongly interacting. So we need some sort of organizing principle. So we know that we can't treat these things independently. We have to deal with the collection. So there's some collective physics going on. So there's some organizing principle. So I need one to start with. Okay, let me just introduce one, and we'll see how far we get with that. Let's assume the organizing principle is scale invariance. And by scale invariance, I mean that it doesn't matter the magnification that you look at something with. The system always, whatever you are looking at looks exactly the same. And this is clear here. Every magnification, you always see triangles. So what if the stuff that is coming out of this strongly coupled soup all looks like this? It's scale invariant. Okay, so what stuff is scale invariant? Let's try to answer that question first. Now, if any of us stand on a scale, a certain number comes about. And that number, if you just back out the acceleration of gravity, will give us our mass. So mass always sets a scale. And hence, anything that has mass is not scale invariant. So the stuff that we want then, if scale invariance is the ultimate working principle, cannot be particle-like, because all particles have mass or charge. I know some of you are saying, well, what about the photon? Okay, that has mass 0. It has a well-defined mass, namely 0. What I want is stuff that has no definite mass. Okay, so however the system is organizing itself, it can't be based on anything that looks like a particle. Okay, so whatever this strange metal is that's carrying current, whatever is carrying the current can't have any particle content. Okay, now how's that possible? Okay, let me just introduce one more notion. Let's just look at units. Since we're dealing with scale invariance, we can't really be dealing with any details. We have to be looking at sort of global structure. Okay, so if we look at volume, volume scales as length, 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 length to the third power. Okay, so just a product of 3 lengths. The area is scaling like L squared. Now, all of this is very intuitive. Something that's not intuitive is, for example, what are the units of the current? Well, there are certain principles in physics that we can use to establish that, because the current is one of those things that's based on a conservation law. Namely, can't destroy or annihilate, create or annihilate charges. And from that basic principle, we can determine that the units of the current have to be similar to volume, except it's the inverse, L to the minus D. D is the number of spatial dimensions. So those are the units of the current. Okay, the number of spatial dimensions. Now here's the key idea, that whatever is carrying the current inside this strange metal is giving rise to a current which doesn't have these units. So somehow the symmetry principle does not apply, or it can be circumvented in some way. And I'll tell you how. Now, why do I want this? Because several of us have shown that if the current does not have conventional units, you can explain all of the electrical and magnetic properties of this strange metal. And hence it's exploring how it is that the current might have unconventional units. And that's really what I want to tell you about. And in showing you how the current can have unconventional units, you will understand how there has to be an extra dimension. At least that's the goal. And if you don't understand that, you should ask me questions. Okay, so how can the current have strange units? Okay. Well, one way is just to look at this equation and say, well, D just isn't what you thought it was. Okay, so it isn't really governed by the total number of spatial dimensions. Only some of the dimensions are relevant. If you were to say that, that would be wrong. It turns out this doesn't work. Okay, you can't explain all of the properties with this particular mechanism to change the dimensionality of the current. You need something else. You need something deeper, more fundamental. Okay, so what's the more fundamental reason? Now, to do this, I just want to tell you the basis for electricity and magnetism. We know that charges produce electric fields, and we're all familiar with this. Magnets produce magnetic fields. And these were thought to be very different phenomena. Until Michael Faraday came along, and here he is on the 20-pound note. They put scientists on money in Europe, not in the States. Okay, and what he showed is that electricity and magnetism aren't really independent. If you move a charged particle, it produces a magnetic field, and hence there has to be a synthesis of electricity and magnetism. There has to be something more basic than trying to worry about the E field and the B field. There's really only one thing you need to worry about, and it's that synthesis that is at the crux of my construction. Okay, so to introduce that, I need to have another interlude on what we mean by moving. Okay, so here's a little interlude on momentum and waves. So here's a wave. the distance between these two peaks is the wavelength. And what I want to do is just stretch this out, keeping the height of the wave the same. So if I stretch this, and so this is called a wavelength, okay? Okay, so I stretch this out. I then want to ask you a question. Say you were swimming in the ocean, and you saw a wave that looked like this and one like this. Which one would carry you to the shore faster? This one or this one? The top one. It's obvious, right? Because there are more humps. And when you ride this wave, every time you get a little jiggle in your motion, and hence you'll be moving faster when you get to the shore. You're moving faster when you get to the shore, your momentum is bigger. Okay, so here we've derived a fundamental principle. The momentum, as you stretch this wave out, the momentum's going down. So we have a very important principle, that the momentum is proportional to 1 over a length, 1 over the wavelength. Okay, this is a very simple derivation of a principle which won a Nobel Prize by de Broglie. He was the first one to think about this sort of relationship. So anytime you see momentum in the rest of the talk, you need to think 1 over length. Okay, now another interlude is on symmetry. If I look at a circle, all the points are completely equivalent. So let me do something that breaks this symmetry. Let me put a dot right here. Okay, now all the points aren't equivalent. So if I were to rotate this like this, this would be at the bottom. And you say, well, this looks different, and you would be correct, which means to get back to where I was, I would now have to rotate it like this, which means there is a new symmetry principle now. All the points are not the same, but they are if, in fact, I define this angle here, and if this angle is increased by 360 degrees, I end up with the same thing. That means it's just gone all the way around. Okay, now symmetries always look like this. Symmetries are ultimately redundant descriptions of a system. So once I change this angle by this amount, I end up with the same thing. Now the symmetry principle in electricity and magnetism looks like this. It's something plus whatever keeps the system invariant. Okay, so there's a synthesis. Electricity and magnetism now arise from some more basic quantity. And that quantity, I'm going to use the symbol A. And we call that, for lack of a better name, this. You don't need to worry, just remember the symbol A. So all of the equations of electricity and magnetism have a symmetry. And that symmetry says that I can translate A by something. Just like when I have this circle with this dot and I can translate theta by 360 degrees, I come all the way back to where I started. So what leaves all of the equations of electricity and magnetism invariant? This question mark is related to this momentum. It's momentum times something, and that thing you don't need to worry about because it doesn't have any units. Now this is important. The momentum has units of 1 over length, which means that this field here, this vector potential, this A, has units of 1 over length. So this symmetry does more. It's not really decorative. It's really telling you that it's fixing that the symmetry is fixing the dimension of A. And it's dimensions that I'm playing with, so which is why I had to walk you through what is the basic symmetry principle in electricity and magnetism. Okay, now so far, you might think this is just a game, some new field, some new quantity. But I want to show you that this is really a fundamental thing that has physical consequences. And this relationship is the key. So if we were thinking about electricity and magnetism, the most basic thing in electricity and magnetism is this new quantity A, and all of the rest comes about from various ways of looking at A, various relationships they have with this quantity called A. You can derive the electric field, the B field, and the current is also determined by A. So this is the sort of thing we like in physics. We look for a unifying description, and A unifies electricity and magnetism. Okay, so the current can have strange units if A has strange units. Okay? Now, how can A have strange units? Now, given that this and this I mean, A gets its units from the momentum, which is units of 1 over length. This symmetry has to be modified. Otherwise, there is nothing that we can do. Okay, so what's the solution? Okay, so we have an equation here, a symmetry relation, which we know can't hold if the current is going to have new dimensions, at least not the traditional dimensions. Okay, so what we need to do is change this relationship in some way. Well, let's assume the same relationship basically holds, but we have to do something sort of tricky. If you assume the basic relationship holds, but you do something tricky, the only solution is that you raise the momentum to some power, and you allow that to be not a whole number. And you're probably wondering, what does all that mean? Okay, so you already know what length cubed means. Anytime something occurs as a power here, it's just multiplying whatever is here that many times. For example, if this were 2, 3 times 3 is 3 squared. Okay, so I'm going to assume now that electricity and magnetism in this strange metal is not governed by the standard symmetry principle, but this one. Okay, so is this new symmetry detectable? If it isn't, then I have no way of falsifying what I've just told you, and hence I will not be doing physics. Okay, so it is. So here's the experiment. If you take a cylinder and you pierce a magnetic field through it in such a way that the magnetic field does not leak outside the cylinder, so the only place that has the magnetic field is right here, you can ask the following question. If I send charged particles around it, do they know about the magnetic field? So do they know about the magnetic field? Okay, and this was a question that has been asked a zillion times in physics. We know what the answer is. And if you live in a classical world, the answer is very simple. If these things don't see any magnetic field, they don't know about the magnetic field. So in a classical world, the answer is no. But we don't live in a classical world. We live in a quantum mechanical world. And it comes about because particles are waves, which means although the paths that they take might not intersect the physical magnetic field where it is, the fact that they're wave-like hence means that they will in fact encounter the magnetic field. So this wave will go through this region. And the only thing that can change about the wave when it encounters this is how much flux there is going through this this tube. The flux is always equal to whatever is flowing through it times the surface area. Okay, so we know exactly what the answer is. So, and this is called the Aharonov-Bohm effect. Now, and it tells you that the waveform here is modified by the magnetic flux. Okay, so in this right here, we know that the flux is just B times the surface area, and this is some modification by the waves. But remember now, since the basic thing in electricity and magnetism is A, I have to be able to relate all of this to A, because that's the thing that gives rise to everything else. Okay, so in fact, if you just have this loop and you multiply this length by A, you will in fact get the same thing as if you had as the field times the surface area over here. Okay, and this is the Aharonov-Bohm effect. So, and what this is telling you is you've related now the magnetic flux to this field or this symbol which you introduced to unify electricity and magnetism. So it's not just some mathematical construct, it really does have physical content. Okay, now if this is true, a lot of things change. Now you've all seen t-shirts that look like this, in which Maxwell's equations are on the t-shirt. Okay, if this is true, God no longer said this. All of the equations change fundamentally, and this is no longer equal to this, and hence the Aharonov-Bohm effect has to change. And if it changes, we can go and calculate exactly how it changes, and it's equal now to the old Aharonov-Bohm effect times something which depends on not just the area here, but the outer radius, and hence the total dimensions of the sample and that funky power we had. This calculation was done by a graduate student of mine, and he looks like a very imposing character, and he is. His name is Tor, the Singaporean god of calculations. Okay, so now this thing can be measured. So my point is this claim that what is carrying the current no longer obeys the standard rules of electricity and magnetism can be tested, because this thing can be measured experimentally. And this quantity depends on the size of the sample. If it depends on the size of the sample, it really is telling you about some sort of physics, which isn't really based on some local region, but the whole sample, and hence it's a non-local effect. Let me tell you what I really mean by non-locality. Now here is a compact object, a sphere, and what do we mean by non-locality? If these 2 points, the furthest points away in the sphere, talk to one another, so if your theory somehow says that these 2 points know about one another, then there is non-locality. Okay? Now, let's look at where does this non-locality come from? All we've done is just raise this thing to a certain power, and that thing is not a whole number. Okay? Let's look at the momentum. Momentum is related to the velocity. And all the theories we write down in physics are based on something having to do with the momentum in a simple way, not in this way. And why is that? Okay, momentum is related to velocity. Velocity is related to speed. How would you calculate, if you knew the distance you were traveling and the time, how would you calculate the speed? Well, you just divide distance by time. And you might get something that looks like this. You might get something like this, or something like that. And all of these are getting closer to this axis in which the distance isn't changing, and hence the speed is decreasing along this as you go from here to here. So the distance is really, the speed is just the slope of these lines. And to get the slope of a line, you can just take 2 points. And these 2 points can be as close to one another as you want. Since this is related to momentum, the momentum is inherently local quantity. Okay. If, however, this is the quantity that you have, where this is not a whole number, understanding this quantity requires information over the whole sphere. It can't be determined by just 2 points arbitrarily close to one another. And hence, this is inherently telling you that your underlying theory has to be non-local, which is something new. Okay, now what kinds of theories have non-locality? Okay, now all of you came here with your programs. So I want you to get those out, and I want you to flatten them as much as you can. So just make it so it's just, you have to sort of get rid of the crease. Okay, so this is really a plane. It's two-dimensional. Okay, and I want you to put your thumbs someplace close to the edge of both of them, like this. Okay, and I want you to bend it inwards. Okay, as you bend it inwards, let me just bend mine so that sorry, I didn't bend it very well. It doesn't really matter. The thing I want you to notice is that these 2 points, which aren't connected, are very close to one another. Which means if I had a theory that lives entirely on what is left of this surface, and I wanted to get from here to here, I would have to build a bridge or something like this. Let's call that a non-local interaction. However, what have I done by deforming the paper like this? It's no longer living in the plane. It's actually living in now the third dimension. So this non-locality appears non-local in a lower dimension, but now in the higher dimension, I can go from here to here without building a bridge, just by sticking on the surface. So if you have a theory which looks non-local, it's telling you that if you were to go to a higher dimension, it might in fact look entirely local. So if in fact the underlying theory of the strange metal looks non-local, it's telling you that locality is recovered in a higher dimension. Okay, so one can formulate that completely mathematically, and you can in fact show that if you start with any space-time, I've just drawn one that is curved in this way, and you might have a black hole in this space-time, and you start with stuff that is entirely local, what you have at the boundary always looks non-local. And it will always look like this thing. And this is independent of whether or not you're looking at copper or not. It's really a statement about things which look like this. And things that look like this came from a space-time which had one extra dimension. Okay, this was done with a collaborator of mine, Gabriel Lanave. Okay, so non-locality is the key. Non-locality is the sign that an extra dimension is lurking about. I've shown you that this non-locality can explain the properties of the strange metal. It's also present in quantum gravity. Okay, so are these two things equal? I certainly think so. But I think to be on the safe side, I would just have to say perhaps. Okay, so that is the end of what I wanted to say, but there's one more thing I did want to say. Okay, today is not a simple day. Today is August 4. Does anyone know the significance of August 4 in US history? In particular, does anyone know the significance of August 4, 1964? No, it's not. Thank you so much. I'm way older than this. Not way older, but some. No, Obama was born in 1961. Okay, so to my mind, the most monumental things in the last 50 years that the US has encountered happened on this day. So here's the New York Times from August 5th. So the two things which happened on this day was this claim that the North Vietnamese had fired on the Maddox, and the US responded by bombing North Vietnam. It became clear that, in fact, this was not the case. So that was the start of that war. And this other headline is that the FBI finds 3 bodies believed to be the civil rights workers. And that's really what I want to focus on. You might remember the movie Mississippi Burning. It started with the murder of these 3 people. Their bodies were found August 4, 1964. They went down into Mississippi to register black voters, and they were killed by the Ku Klux Klan. One would have hoped that we would be further along than we are now, but we aren't. And I just want to put up to you 2 quotes. And it's interesting. They're basically saying the same thing. And the reason I want to bring this up is that this one particularly points out what unique perspective does a minority student bring to a physics class. And this one that says most of the black scientists in this country don't come from schools like University of Texas. They come from lesser schools where they don't feel that they're being pushed ahead or that are too fast for them. Now, you might think this is coming from a fringe, but it's not. These are coming from the justices on the Supreme Court in a case that they decided recently. It would certainly be my hope that if there is a public lecture I give in the future, this is not the thing that I close the public lecture with. But I just wanted to mention August 4, 1964, that I hope the lives of Cheney, Goodman, and Schwerner were not in vain. Thank you.
All right, now the floor is open for questions. Yes, sir. Phil, why don't you handle Coulomb, whoever you want, okay?
Okay, fine. Yes.
Lisa Randall's theories of additional,
Okay. Yes.
are they just a higher order of the one you put up there?
Okay, so since this was a public lecture and I'd leave out all the details, the paper we wrote on all of this highlights the construction by Randall and Sundram. And it shows, okay, so why does this theory look so strange? I claim it looks strange because gravity is inherently non-local. Okay? And that the way that you get rid of this non-locality is to put something in the space-time that blocks you from a free fall into that particular location. In the Randall-Sundram construction, there's a singularity in the space-time which gets rid of this non-locality. So your question is absolutely right on, and if you want to read more about it, you can look at the paper that we wrote. Okay. Yes?
When you're talking about superconductivity, do you think that there's something akin to a Moore's law, that the temperature at which your work is going to get higher?
There doesn't seem to be anything like that. In other words, as far as we can tell, there's no ceiling. And the scaling is certainly not so systematic as Moore's law for the efficiency of, as you make semiconductor devices smaller. Okay.
The number of papers doubles it.
Yeah, the number, yeah. There's probably on the number of publications and the size of people's egos, but certainly there's no limit on, we would like to think that that nature does not have a ceiling on the superconducting temperature. Okay? But that's a very good point. Yes?
Have there been any observations of or use of something like, say, palladium at superconducting temperatures with hydrogen in crystal lattices?
Okay, now you clearly asked that question knowing that the answer is yes.
Oh, I did not. I swear.
Oh, okay. I mean, I couldn't have planted a better question. Yes. Under high pressure, we know now that hydrogen there are claims of superconductivity and at incredibly high temperatures, above room temperature. But the pressures that you need, it's not ambient pressure like you walk outside now. It's on the order of gigapascals. Okay? So these are not small temperatures. So the utility of that is still, you trade off the cooling for now pressure. So it's not exactly the most useful thing if you want to make superconducting wires out of this. It's just not really feasible. Okay. Yes?
Have you detected a pattern in the different types of superconducting materials? In other words, it looked like there was a group of copper, and then you had, I noticed, some iron ones that got toward the right side of the scale there.
Right.
And can you predict from that pattern where you might find higher temperature superconducting material?
Okay. On that, so maybe this graph was a bit misleading because so let me just tell you what the actual thought is, okay? The iron-based superconductors, which superconduct at temperatures lower than these copper oxide superconductors, those were discovered in 2005 in iron. Now remember, magnetism and superconductivity don't like one another. So the last place you would have looked would be a material containing iron. And so if anyone tells you they have a predictive theory for what will be a superconductor, just don't listen to them. Okay, so there doesn't seem to be any sort of rational scheme. I mean, superconductivity is probably the weirdest phenomenon on the planet, and there's no sort of systematic way of synthesizing something in the lab that you borrow from this idea. We can sort of mix various things, and we're getting some idea, but in terms of a systematic, that is the one thing we definitely do not have.
And are the elements that you're looking at, I mean, these elements that you're using, I noticed there's like ytterbium or something in there, barium,
Right.
strange, rather unusual.
I mean, they're now rather common, but ytterbium is not so strange, really. It's just one of the rare earths. Rare earths are not that rare. Okay? So I think you and then...
At what temperature will superconductors have to rise to make it economically feasible to rewire America?
Okay. So right now, there are power transmission plants that are connecting superconducting wires from them to transformers. And that is certainly taking place in Germany. There is one place in, actually there are several places in New York and Chicago. It's coming to a city near you, okay? Well, it's the refrigeration that is cheaper than beer. Liquid nitrogen, 77 degrees Kelvin. Yeah, the liquid nitrogen is part of the cooling is part of the wire itself. And that's a picture I got from a German company, actually, that is using that between the power plant and the transmission. So that's everyone should be interested in superconductivity. Your electrical bill will go down, okay? And we all want that. Okay, yes?
There's an alternating current superconductivity. Is there?
Yeah, there's no difference. Yeah, it doesn't matter. Yeah. Yeah.
Maybe you should mention the super collider uses superconducting magnets.
Yeah, it uses superconducting magnets, but those are not the cuprate-based ones. That's still liquid helium technology. But in principle, there's no reason why they couldn't use the copper-based superconductors. Yes?
If you're able to ascertain that copper or these cuprates have extra dimensions and develop a theory that will explain their superconducting behavior, does that give you the power to subsequently go back and design new superconductors at different temperatures?
Okay, that is what we say when we write our grant proposals as the reason why so many theorists have worked in this field. And the hope is that if you have, I mean, it's physics, so if you have a rational analysis, then that should take you somewhere. So that is the hope. The previous theory was a non-starter for these new materials because their starting point is just not valid for these new materials. So the hope is that we have something that in which the interactions dominate, we have a theory there, then we have the two limits, pretty much all bases are covered, perhaps then we could predict something. Yes?
Power plants and substations that go to transmission voltage are close together. They're just outside the
Right, yes.
And the reason for that is the cooling combined with the distance of short.
Okay, but in Germany, however, remember now the cooling is part of the wire.
Right.
So that can stretch fairly long distances. And the one in, I think it's not Upton, New Jersey. I forgot the name of the city in upstate New York where, in fact, there is a power plant that uses superconducting wires. The goal is to really start replacing the wiring. So as far as I can tell, it is not as far-fetched as we might think it is. Yes?
What about using silver in place of copper?
Ah. Interesting that you would ask that question. Okay. When I started this field,
What was the question?
the question is substitute silver for copper. Okay. So when I started working on this field of high temperature superconductors, everyone said copper is really important. And I wasn't convinced of this. I'm a theorist, but I was a chemist a long time ago. So I went to the lab.
You said this, not me.
Yeah, I know. Okay, so I went to my friend Russ Giannetta's lab, borrowed his oven for a few days, and made all I did is substitute silver for copper. and it was an absolute disaster. It does not superconduct. So it was at that point that I began taking this whole thing seriously, because I thought, my goodness, silver should be just as good as copper, because someone had some theory that copper didn't have the charges that it really had, and magnetism really was not important. So I said, well, just go and do it. So I went and, made the material, and at that point, I started taking the whole field seriously, and that led me from that point, that failed experiment with silver, to higher dimensions. Yes?
Do you happen to know the temperature of liquid nitrogen in Fahrenheit?
Liquid nitrogen Fahrenheit. Yeah, on minus, sorry, no. Why did you ask that, Dave?
Because people might get a better sense of how...
Okay, so I gave this talk to my research group, and they said, make sure you have the temperature for 0 degrees Kelvin in Fahrenheit. But I could go and compute it, but no, I don't.
It's cold, though.
It's cold, yeah, it is cold. It is cold. Yeah, I forgot the number.
But the rest of the world uses Celsius anyway. We should use...
But we know what it is in Celsius. It's minus 197 Celsius, so, right. Yes?
You said that the superconducting wires are being used, but to what length? You said
Okay.
more than 10 feet, but
Yeah.
100 miles. And how would you get that coolant to stay cooled that far?
Okay, I have seen claims of quite some range. I would encourage you to Google this yourself. Okay? There are things going on in Japan that claim incredibly long distances. I don't really know how true that is. But this is where people are pushing this whole technology. Yes? Minus 321. Excellent. Thank you, David. Minus 321 degrees Fahrenheit. Yes, that's right. Okay.
Well, maybe we should thank Phil now, and you can meet him after.